Hey folks, let's take a look at one of your homework problems, finding of area and polar coordinates. This is one where there was a common interior to two polar graphs. In your text, it was number 39. You were asked to determine the area that is the common interior of r equals 4 sine 2 theta and r equals 2. By this time, you should know that your first step in doing this solution is to sketch a graph. So when I use my graphing calculator, again, I'm using the TI-84. This is the graph I get. And of course, my theta min is 0. My theta max is 2 pi. Um, so we're trying to find the area that is the common interior of this rose curve. There are 4 petals of the rose curve, and the circle, r equals 2. Looks like there's 1, 2, 3, 4 regions that we need to find the area for, one in each quadrant. But what we're going to do is if we can find the common interior for just one of these 4 regions, then all we have to do is take that result and multiply it by 4, and that'll give us the entire area, the entire common interior. So first thing first, we have to find points of intersection. And points of intersection here will be found by equating the two polar equations to each other. R equals 2, R equals 4 sine 2 theta. So if we just set up the trig equation 4 sine 2 theta equals 2, this will allow us to find points of intersection. Divide both sides of this equation by 4 gives us sine 2 theta equals 1/2. And in the prior video, as we saw, I kind of look at this equation as sine of what is equal to 1/2. So, it doesn't matter if this is called 2 theta or 5 theta or 7 theta, or you could call it Fred if you'd like. The sine of what equals 1/2? Well, from the unit circle, I know the sine of pi over 6 and 5 pi over 6 will give me 1/2. So that means here the 2 theta has to be 5 pi over 6, or 2 theta has to be, well, pi over 6 or 5 pi over 6. That's one trip around the unit circle. My little trick, because of the 2, let's make a second trip around the unit circle, and that gives us the angles 13 pi over 6 and 17 pi over 6. Keep in mind to get these two angles, they're just coterminal to those two, and so you just add 2 pi to them. So divide everything here by 2. That'll give us the values of theta of pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. These are the thetas where we will have points of intersection. Now, if we redraw, this is an old process hopefully by now, you redraw your polar equations. Since I saw one of the common interiors was out there in quadrant 1, I'm going to redraw with a theta min of 0 and a theta max of pi over 2. That better produce that region we saw in quadrant 1. If it doesn't, something bad is happening. I also know that those points of intersection out in quadrant 1 occur at theta of pi over 12 and theta equals 5 pi over 12. And I go ahead and I use my graphing calculator to redraw the graph with a theta min of 0, theta max of pi over 2, and this is what I get. And again, those are my points of intersection. I know the theta value of those points of intersection are pi over 12 and 5 pi over 12, and they'd have an r value of 2. But I'm a little concerned as to what's happening in this region. I feel like it could be a little tricky. In fact, I know it is a little tricky. So what I'm going to do is I'm going to zoom in a little bit more on that region. I'm going to regraph it on my calculator on a smaller viewing window. I'm going to go like 0 or negative 0.5 to I think 4 on the x-axis and negative 0.5 to 4 on the y-axis. So I'm going to redraw it. And here's a look at the graph. Now see, the reason why I thought I wasn't quite seeing what was happening here, but I kind of see it now. that this region here, it looks like when I draw in the radial line theta equals pi over 12, I'm going to get a little sliver down here that's bounded by the polar curve. From pi over 12 to 5 pi over 12, well, the common interior is bounded by r equals 2, the circle. And then from 5 pi over 12 to pi over 2, it looks like that little sliver there is again bounded by the Rose curve. So if I drawn in the theta equals pi over 12. Now, I had a little trouble trying to draw it perfectly, but you can see what I'm getting at. There's a little sliver here that is bounded by the polar curve that's giving us the rose petal. And if I sketch in the 5 pi over 12, and again, I kind of missed the point, but I think you see what I'm getting at. This little sliver is bounded by the rose petal and the polar curve that's producing that rose petal. But between pi over 12 and 5 pi over 12, we're bounded by r equals 2. So it looks like that to get that area in quadrant 1, I'm thinking I'm going to need 3 separate integrals. An integral that's going to find this little sliver, an integral that will find this wedge, and then an integral that will find this little sliver here. And, well, this is what we'd have to do to find that area. 1/2 the integral 0 to pi over 12 r squared, 4 sine 2 theta, quantity squared. That's that little sliver here that's bounded by the polar curve. R equals 4 sine 2 theta. And then this piece in here, limits of integration are pi over 12 to 5 pi over 12. R is 2. This will be a really easy integration problem here. And then finally, this little sliver here is found by 1/2 integrating from 5 pi over 12 to pi over 2. The Rose curve, 4 sine 2 theta, quantity squared. Now, I think that this little sliver here is found by this integral, and that little sliver here, which is found by that integral. I think those two have the exact same value. So since I think they are the same, I can use symmetry. That's exactly why they're the same, is using symmetry. And I should be able to rewrite these 3 integrals as simply doing 2 times 1/2 the integral pi over 12, or 0 to pi over 12, 16 sine squared 2 theta. In other words, well, 4 sine 2 theta quantity squared gives us the 16 sine squared 2 theta. But if I take this and I multiply it by 2, that's going to find this area here, that little sliver, and that little sliver there. And then, well, 2 squared is 4. Again, that's going to be a really easy integration problem. Continuing on, just bringing the problem on over to the top of this slide, and cleaning up just a little. We know 2 times 1/2 is 1. Rip the 16 out front, and then well, sine squared 2 theta. I can't stress enough how important it is to remember those power reducing identities. To remember sine squared x equals 1/2 times the quantity 1 minus cosine 2x. So the sine squared 2 theta, thanks to the power reducing identity, becomes 1/2 quantity 1 minus cosine 4 theta. And then I'm just bringing this one on down. That's going to be a real easy calculus problem, in case I haven't mentioned that already. As you could probably guess, I'm going to rip the 1/2 out front. 16 times 1/2 will give me an 8. And then doing the calculus, antiderivative of 1 is theta. Antiderivative of cosine 4 theta is 1/4 sine 4 theta. We'll have to evaluate that from 0 to pi over 12. The antiderivative of 4 is 4 theta. 1/2 times 4 theta gives me 2 theta. So now cranking these through the fundamental theorem of calculus gives us this. It looks like a mess. Hopefully it'll clean up nicely. 8 times pi over 12 minus 1/4 sine. When pi over 12 comes in here for theta, we get a pi over 3 minus tossing the zeros in for the thetas. That's not too bad. Plus 2 times, 5 pi over 12 minus 2 times pi over 12. And cleaning that up just a little bit, sine of pi over 3 is square root 3 over 2. So 1/4 times square root 3 over 2 gives us square root 3 over 8. All of that's 0. So 8 times 0 is 0. 2 times 5 pi over 12 is 5 pi over 6, and 2 times pi over 12 is pi over 6. So doing a little distribution here and combining those terms, since we already have a common denominator, gives us 2 pi over 3. 8 times pi over 12 is 2 pi over 3, minus square root 3, plus 4 pi over 6. So now if I get a common denominator here, 2 pi over 3, well, that's 4 pi over 6, or 4 pi over 6 reduces to 2 pi over 3. You can combine those two terms to get 4 pi over 3 minus square root 3. So 4 pi over 3 minus square root 3, that is the area of the common interior that we saw out in quadrant 1. So the total area, since that same common interior was in all 4 quadrants, the total area is found by simply taking 4 times what we just saw was happening in quadrant 1. So 4 times that mess, 4 pi over 3 minus square root 3, gives us a total area of 16 pi over 3 minus 4 square root 3. I think without a doubt the most difficult part here was setting up the original 3 integrals. Being aware that you needed 3 integrals, getting the points of intersection, knowing the theta for the points of intersection, and then accurately setting up the 3 integrals. We are done. So I hope this helps shed a little light on number 39. And I thought it was one of the more challenging ones in the homework. And I hope this helped. Thanks for watching.